Hi guys, welcome to Learning Electronics Repair. If you're a regular viewer, you will have seen this a few weeks ago. This is the LG subwoofer, and we had a couple of burnt out resistors on here. I couldn't find anything else that was wrong with it, but I presumed that the fault was in the controller chip that drives the switch mode power supply. So I had to order some. Couldn't get any from the electronics shop in the capital here, and the good news is the replacement ones have arrived. I ordered a pack of 5, so we have a few chances at fixing this thing. So let's have a close look again to see where the resistors were that I removed. Let's have another look for any possible damage, and then we will replace the part. We will connect the current limiter, the light bulb, and let's see what happens. This is where the controller chip was located for the switch mode power supply. This actually has the pulse width modulator controller and the MOSFET built in one. So basically on here you will have the high voltage from the mains rectified and smoothed off the capacitor, so 320 volts or something coming in through the coil of the transformer, the primary, and then the MOSFET to ground. I think these 2 pins at the back are probably part of that. They normally put them further away than the other ones because they have a high voltage on, so maybe that one and that one. Obviously the datasheet would tell us, but no harm in just surmising. Yeah. You'll have a VCC pin which powers the chip, probably 15 volts, something like that. You'll have a feedback, you'll have a current sense, and the current sense was measuring the voltage across these 2 resistors. These are blown, they were open circuit. Each one is 0.22 of an ohm. In parallel gives you 0.11. Having removed those, I can't find any shorts anywhere. There was no shorts on this chip. I'm assuming at the moment that when it blew, that it actually effectively went open circuit due to the same current that caused those to blow open as well, and the short, if it was a short, is no longer there. Let's have a quick look around as well, because 1 or 2 eagle eye subscribers did spot something I didn't spot, and that was with this capacitor. So let's have a look at that. So this capacitor, you can see, has also blown. These high voltage capacitors very rarely fail, but this doesn't look good at all. We'll check to see if that reads short. Let's just get the multimeter, and then we'll have a look to see where this is in circuit as well. Okay, I'm on ohms, but on continuity range, so it will bleep. Let's see what this capacitor reads. Well, it reads open. I'll go into resistance range. Definitely reads open, but this is obviously failed. Let's see where that is in the circuit. It's next to this diode. Okay, this diode is part of the snubber network. I'll find the datasheet in a minute, but you'll be able to see how this actually connects up. What it looks like, this capacitor here, it's quite near to this hole where the heatsink fits, you can see, which is there. So that's the capacitor. One end of the capacitor goes to the current sense resistors. These are the ones that were blasted. In parallel with these, there is another capacitor from here to here, and there's a reverse biased diode. It's reverse biased because this is your main smoothing capacitor. So this is the negative end, and it's going to the cathode. So that diode would only conduct if this point became more negative than here. Okay, and the only reason that sort of thing would happen would be due to some back EMF in the coil, I would say, but that's what it's there. It's not actually doing anything, that diode, particularly. Somebody else can probably say, yeah, I wish it's exactly for this reason. And the diode reads okay. This point then is where the current sense is measured across these. And the reason you can't see a connection into the current sensor is because it's actually built in this chip. So the source of the MOSFET is also the current sense. I'll show you the datasheet and you'll see that's obvious. This is the drain. So this connects via, there's a ferrite bead here. Through here, this is your transformer primary, and the other end goes to the positive end of the capacitor. So effectively, that capacitor is connected to the drain of the MOSFET. And this is what's blown. This kind of supports what I thought originally, that the reason these have blown, and that looks like it's blown as well, is because of some sort of massive back EMF from the transformer, which probably happened because this chip failed and drove it into saturation, so there's a very large magnetic field in it. The MOSFET in here then went open, and that field collapsed, and because it was much higher than usual, it blew these resistors and blew this capacitor. That's possibly, again, you know guys, comments below. I love analysing this stuff, and I love to hear what you guys think. Also, I'll change that capacitor. There's another capacitor here. Now, when these went open circuit, that would be subjected to a high voltage across it. Normally, with these low value resistors, they're in parallel with the capacitors, so there's practically no voltage across it. I'd be interested to see what that capacitor looks like. Well, it's here, it's like a little bead type thing. Looks like it's subjected to something because that looks discoloured. Let's see. Yeah, if you look at this leg here, it looks like a lot of currents flow through here, so this could be faulty. I think we'll take this one out and measure it. If I just put the meter back on screen, you'll see it reads, on continuity mode, it reads open. Ohms range also reads open. So it doesn't read like a bad capacitor, but we'll take that one out, and this one we'll take out so we can see what the markings are on it. This diode is part of the snubber network, so this is supposed to effectively deal with these high voltage back EMFs. That's the actual bead under there which we were talking about. Let's look at this diode. Yes, it's here. So one end is connecting to the drain effectively via this ferrite bead. It's connecting to the end of the coil, that's where you'd expect it to go. And the other end via a resistor and a capacitor connected to this point, which you can see goes back to the positive of the main smoothing capacitor. The diode itself, well, let's have a look. This end to here, this is the positive, yeah, that reads like a diode, okay. And then the resistor here should be probably fairly high value. We can look at the markings, but 50k, 100k, something like that, you know, 55k. That's exactly what I would expect that to read, to be quite honest. So that looks okay to me. Let's just put that on a piece of paper so it's obvious. Here is a block diagram, but it also shows how this chip connects up. Basically, you can see it's a very simple circuit. Ours has a few slight variations, so I'll just draw those on here and explain where the damaged components were. This is the snubber network which I described, but I'll actually draw it. So what we actually have here, we have a diode connected like this, and then from here we don't have enough space to draw it, so we'll just draw it like this. We have a resistor, this is what we read, about 55k, and we have a small capacitor across there, and these connect back to here. Okay, so that's what we have. This read 55k, which is about right for this sort of thing. You'll notice that this diode is actually reverse biased because This is the cathode, and this is the positive end of the large smoothing capacitor, which via the resistor comes to the cathode, and the other end goes to the here. This is the drain, this is the switched end of the primary. And as I mentioned, this is to effectively handle large voltage spikes here. So when you switch the MOSFET in here on, you pull current through the coil, that magnetizes the coil, but before it can become fully magnetized, you switch off. Once that happens, the magnetic field collapses, causing current to continue to flow in the same direction. And because current is flowing from here to here, this end actually becomes more positive than this end. And this diode is now forward biased, and it removes the large positive spike. That's what that actually does. It's called a snubber network, and it's made of these 3 components. Those read okay. The diode's okay. The resistor, I didn't look at the markings, but 55k is perfectly reasonable. The other difference we have is down here. So this is the sense resistor. We have, in actual fact, 2 resistors in parallel here. Each one is 0.22 ohms. Times 2 of them. We have a capacitor here, which looks like it may be damaged. Can't say for certain. It reads open circuit. And we also have a diode here, wired this way round, reverse biased again in normal operation. And this reads okay. As I mentioned, these low value resistors are in the current path through the transformer winding, so through the winding, through the internal MOSFET and the chip, down to here and to ground. And basically, this sensing circuit, this current limiting, measures the voltage across the 2 resistors. So normally, because these are such low value resistors, the voltage between here and here is practically 0. Not quite 0, because obviously there is something to measure for the current sensing, but less than a volt maybe. When these went open, it's possible that that was damaged. Also, this could have been damaged. It depends on whether that diode can handle the reverse voltage. If it's a 400 volt diode or something like that, it will be fine. And it appears to be fine, so it probably is. So we'll take that capacitor out and have a look. Let's measure it out of circuit, see what it looks like. If I can read the value, I'll probably replace it anyway. The other diode that looks like it's damaged, well, that goes from the drain here to here. So we have a diode. I'll draw this as though it's coming from inside the chip, but it's the drain, yeah? So that other capacitor effectively connects from here, here. This is a lot easier when you're not looking at the magnified screen, by the way, to there. And that's the one that's blown a hole in it. So what I think has probably happened to this is something's gone wrong. The MOSFET has turned on for too long. Therefore, this coil has become fully magnetized. At the point this becomes fully magnetized, this is called saturation. It can no longer limit the current that's flowing through it. So it acts like a short. That has then caused a massive current through here, the MOSFET and these resistors. It's blown the resistors, certainly, quite probably blown the MOSFET as well, who knows. But at that point, this has become open circuit. I think that probably blew first, I'll tell you why. Because once this becomes open circuit, this primary field will collapse with a massive surge, which is what I think has blown this capacitor and blown these resistors. And I think these resistors still needed to be intact for that to blow. That's just me doing a bit of Sherlock, but hey, I wasn't watching at the time. What do you guys think? Yeah, if you've got any other ideas, let's know. But it's not really relevant. We know we have a bad capacitor, possibly another bad capacitor, probably a bad chip, and that this all looks okay. I've removed the 2 capacitors. We'll check them in a moment. It looks like this is the one that's blown, that something effectively is arced over here. You can see it. this is then the glue, which is by the inductor bead. Did that become conductive? Can't say for sure, but I think I'll try and remove it. I'll replace this wire link with a piece of insulated wire just to be sure, and I'll try and scrape some of this away to see what's underneath it. The inductor bead reads okay. I've lifted one end of this wire and put a piece of heat shrink on. It probably won't shrink down to that size, but it'll act as a good insulator. I've scraped away this glue. This black, I think, is actually marked on the PCB. Certainly that under there, like I see a black dot under here by the resistor. Okay. The lead to the inductor is exposed there, nice and shiny. That's fine. So we'll solder this wire back down. Now let's have a look at the other components. Here's one of the capacitors. This, just looking at this lead, looks like a lot of current's gone down in there. We can test it, but I wouldn't trust it anyway. And here is the other one, which is obviously not very happy. Yeah, not a happy bunny, as they say. So what is this thing? Well, the marking's on the other side, so 471, so that's a 470 picofarads, I would think. Yeah, I think it's a 470 picofarads, 470, and it is 1 kV. So let's see if we can find anything there. The letter K, I'm pretty sure this is a tolerance. Yeah, so 47 and 10 is the marking, 470 puff, 1 kV. So that we will definitely change. Yeah, that's got a hole in it. Let's measure the other one. I guess it's a fairly low value capacitor. Let's set the range to 200. Let's see what we have. It's reading 120. It's probably a 100 nanofarad capacitor. I don't know this marking, so I can't really say what the voltage is, but I know where it is across those resistors, so it's not going to be a high voltage, so I'll stick something in there. Small, probably a 50 volt capacitor. And I'll see if I can find a replacement for the other one. With the capacitors, I do have one marked 471. It's probably a 1 kilovolt capacitor. It doesn't have a voltage marked on it. This one is 681. And this one says 250 volts AC on it. And this one is 102 and says 1 kV. So if 471 is 470 picofarads, we'll measure one. This is 1000 picofarads, but it's the right voltage. And I'm tempted to put that one in, to be quite honest. I don't think much current flows down here, but I think we might well find out in a moment. So let's have a look to see how these measure. Well, this is the one that says 471. And in fact, 560 picofarads. So I was right probably on that one. This one says 102. So I'm thinking this will be about 1000. Yeah, 1200. And this one, 686. The only thing I'm not sure about this one is whether it is actually the 1 kV, but you know, it's a big, thick, chunky capacitor, so I think it may well be. We need to stick something in here, so it's a matter of which one. I think I'll go with the 1000. I know it's about twice the value of the other one, but we're still talking about very small value capacitors, and it's definitely 1000 volts. Let's see what happens. Here are the ICs, the controller and integrated MOSFETs. I got these from AliExpress. There's 5 the other ones under the microscope. I'll show you in a moment. Somebody commented that they wouldn't trust these ICs from AliExpress. They said they must be pulls, because why did the pins come preformed like that? Well, the simple answer is that that's how they come. I mean, I've ordered them from various places. They always come like this. 3BR0665. And you see one here under the microscope. This gap here is not because a pin is missing. It's because this is the drain. This is the high voltage. I think that one's a source. So it's sort of spread out further away. You can see the idea of this is so that the high voltage pins are not close to the low voltage pins on the PCB. It's to do with the PCB layout, really. And you can see how this is laid out on the PCB also. So to answer that subscriber's comment, no, this is perfectly normal. I've fitted the capacitor. That's the small round one. I found one that kind of looks like the other one. It reads 100 nanofarads. You can see I've put a bit of heat shrink on here, so that should stop any more arcing over. I fitted the two resistors. These are quite a bit bigger than the original ones. These are 2 watt each in parallel. The original ones must have been 1 watt, but I wasn't sure, so I ordered some 2 watts. They fit anyway, so that is not a problem at all. Once we've put the IC back on with the heatsink, we can try this. I fitted the replacement chip. I've had another thought about this. It could just be that this capacitor failed, because one end of this goes to the drain of the MOSFET, which is basically via the transformer winding connected to the positive end of this capacitor, and the other end via the current limiting resistors goes to the negative end. So that has the high voltage across it with some spikes because of the drain where it's connected to switching the coil. If that did fail, then yes, that would have kind of like blasted out over this way and effectively created a short across this capacitor and blown these resistors. If that's happened, it's quite likely the chip itself was okay, but I've replaced it. So let's power this up and see what it does. I'm going to power it up without the load connected at the moment. I haven't, or I don't remember if I did on the first video, check for shorts on the load. I mean, that could possibly cause this to fail, although I'd be a bit surprised it failed in that way. But first of all, let's just try this on the bench and see what happens. When you're doing this sort of repair, guys, connect a light bulb in series with the live or neutral, but certainly in series with the load. This is a 60 watt bulb you see over there, so that will limit the current that can flow into here. Hopefully this will prevent anything from exploding. It may not prevent something from failing again, but it gives you a far better chance. When we switch this on, we would expect the light bulb to come on bright for an instance and then go dim because this capacitor charges up. If it doesn't light up at all, well, there's no power effectively getting as far as the capacitor, and if it comes on bright and stays on, there's some problem. Okay, so let's switch it on and see what it does. Well, it came on bright and then went off, or rather, not exactly bright, but it came on and went off. So that suggests the power supply did power up. There's no load, so it could be running. I think the thing we should do is just check if there's any output, but it does look like there might be some sort of control pin on this as well that maybe would stop it from running. Let's see. We have power effectively between here and here. There's quite a few pins which are power, so we don't need the exact one. Let's switch this on again and see if we have any output from our power supply. And in fact we don't have, okay, there's no output from there. Just switch it off. I'm just going to see whether this capacitor is discharging or staying charged. So we'll go across the bridge rectifier. I should be able to get to is positive to negative. And we see it has 200 odd volts in, but it is dropping. So something is discharging the capacitor. That makes me think maybe this was running to some extent. I think I'll just attach the load. I'll just check the shorts on the load first. And if I'm happy, I'll attach the load and let's see what happens then. we can see we have pins 1, 2, 3, 4 are ground, and there's like a little marker here which shows pin 1 just behind here. There you can see it. Then we have no contact, although there's a wire connected to it, but it doesn't seem to go anywhere on the board. So 1, 2, 3, 4, no contact, and then we have 1, 2, 3, no contact, and this power control. I can't imagine how this works unless it's some sort of like this is grounded when it connects to the board, because there's no standby supply from this from what it's marked. It's all one power rail. Yeah. So without a standby, it can't be anything intelligent switching this on. It may just be that this pin is grounded when it's connected to the load, and that enables a power supply. Let's have a look actually just to see that. So we're on resistance mode. So if we go to ground and power, which would be here. Well, we don't have a short, okay? You can see there's no short there. What's on this one? No, that's not grounded either. It has 10k on it. It has a resistance. Let's go the other way. In fact, let's go into diode mode. Yeah, all the way around. This is reverse polarity, so effectively I've now got the red lead into the ground, so that polarity would never occur anyway. We do see a diode junction, but something clearly is connected to that pin. Okay, there's no shorts on this, so I'm going to power this up again and let's see what it does now. I have this connected up. There doesn't appear to be an on-off switch exactly for this. I think it just has a remote control. We know that there is power getting as far as the capacitor because the light bulb comes on for an instance. I've connected my multimeter across the voltage output. Okay. Let's see what we get. I'll leave the light bulb on for the moment because without a speaker attached to this and no audio input, I don't think it's actually going to draw much power. I'll put the meter onto volts and let's see what it does now. Well, something blipped, but there's nothing coming out of it. And that was my meter actually, that's my soldering iron. Okay, so it looks like the power supply doesn't work at the moment. Let's go to this control pin. Okay, what have we got? Back on. Well, that appears to have 0 volts on it. The light bulb doesn't come back on, which tells me the capacitor is still charged, so there's a high voltage in this at the moment. So from what I can see, we have nothing on the control pin. Nothing on the output. Which is here. Okay, once again, no voltage coming out of our power supply. So why isn't it powering up? That's a good question. I've attached the speaker. There's 2 wires which go into the front of here. This one is the actual speaker, and this has 3 wires on. I don't see any on-off switch anywhere on here. There's an LED on the front, possibly a bicolor LED. I'm kind of assuming that's where that goes, but I don't know for certain. The capacitor is pretty much discharged, so we should be able to try this again, and the light bulb should flash. We'll just connect this once again to ground, to power. Okay, see if we get anything now, and we'll watch the light bulb again. Well, the bulb flashed, so it's definitely getting power going in, but there's no voltage output coming from it. So maybe we still have a problem on this power supply somewhere, that effectively the thing isn't starting. Go back to the bridge rectifier. Something's discharging that. Let's see if this is oscillating. The easiest way to do that is just to put our scope probe near to it. We don't need to connect to it. And see if we can see any spikes, you know, like a high frequency spikes being radiated from the transformer. That's what you normally see if it is running. So to do this, we just use the scope. I haven't got it connected to ground or anything. It's just the scope probe. I'm just going to hold it near the transformer. And this should tell us whether it actually powers up. Okay, let's see. Well, in fact, nothing is happening, okay? Well, guys, looking at the data sheet, there isn't much to go wrong with this. We should have a high voltage on the drain. We can test for that. If it's not there, well, we've got an open circuit somewhere, maybe the transformer coil. I think I checked it before, but that comes directly from the main capacitor. We know power gets as far as here because it charges up. Okay. The VCC power here actually comes from this transformer secondary, the auxiliary secondary, but that is the main supply for the chip. To start it up before the transformer is running, it has this startup cell. This is built into the chip. So this basically is equivalent to a high value resistor, which charges this capacitor up enough to start the chip running. And once it is running, it generates its power from here. If we look at the data sheet, it says the startup voltage, or rather the VCC, needs to be between 10.5 volts and 25 volts as the maximum. So we can have a look on there. That pin is difficult to probe on the chip because it's like buried down inside, but I'm fairly sure I can find this diode or capacitor and I can measure there. It would be easier and safer to measure. So we'll measure on the drain and we'll measure on here, and let's see what we get. Drain is quite easy to get to. That's this one, pin 1, and then buried down under here we have pin 2, 3, 4. So the one towards the back, that is pin 4. And that goes, we can see, to a diode, a capacitor. Oh, and there's a zener diode here as well. I bet this is part of it. The zener just stops the voltage going above 15. That is a capacitor. This is another diode, and there's one here. So I think we're going to find that one of these diodes connects to this pin 4. If I get down inside there, this is powered off at the moment. We're just on resistance range, ohms. So I get onto pin 4. Yeah, it goes to the end of the zener diode, the positive, exactly where you would think it would go to. Okay, so we can probe there. That will also be the positive of this capacitor. And it will come from a diode. Not that one, the other one. Where does that come from? There, positive of this diode in actual fact. So I found, no, that's another zener actually on the same voltage rail. Where does this come from? Well, you would think there's a diode somewhere it comes from the secondary of this transformer. Or rather the auxiliary secondary, where is it? It's a diode here, is that one might be it. So from there to there, 20, no, not there, 28 ohms. Oh, it must be coming from here through a low value resistor by the looks of it. That's not unusual. Let's see if we can find it. Yeah, the zener diode goes to a resistor. It makes sense as a resistor in here because obviously we want to limit the current through the zener when it's regulating. The other end of this is the 18 ohm resistor, which reads 18 ohms. Does that go to a diode? Not there. That's the other zener. It's another zener. Well, there's not many diodes it can go to, and I can only see 2 of them. This is the cathode, this is the cathode. I'm interested to see where that actually goes. I'm certainly interested enough to trace it out before I take the measurements. So let me get this power supply board back off again, and let's just figure out how this is connected. Well guys, I found something interesting. So this is the pin out of the chip. You can see pin 4 is the VCC. Pin 5 is ground, okay? And I just want to show you what I found on the one that I have fitted on this board. And you can see we have drain, pin 1, 2, 3, 4 marked V. This is VCC. And this is ground. And look guys, we have a short. VCC to ground is short. That makes me think obviously there could be something short on the board, but something that's a bit suspicious as I had a look at the other chips that I bought as well. So here are the chips, and you can see pin 4 VCC and pin 5 ground. So I haven't fitted these. Let's just measure across them, okay? So this one reads 760k. This one reads 31 ohms. That one, 31 ohms. This one, pin 4 to 5, 780k like the first one. Okay, and this one, let's have a look. So pin 4 to 5, 820k, higher than the other two. This one 30 odd ohms. So obviously this one is bad. There's something wrong with this one. So I'm going to take out the one I've soldered in before I even try to trace where that short is. I'll see how it measures. Maybe I have some bad chips. I'm not sure they're fake or they poles. I mean, they don't look like poles, but I don't know. This one obviously is different from the other ones, and it's the same component. Okay. I'm a bit suspicious. Let's see what the other one reads. I'll take it back out of circuit. But before I unsolder this chip again, I'll try to do this the quick way. So if I unsolder this pin from the board, I should be able to check whether the short is still on the board with that unsoldered. Another option would be to unsolder one end of this wire, which I think is a wire, W903. Yeah, it's a wire link. You see it there. So I could try that as well. It's another possibility. But if I do unsolder this wire and the short is still here, it could also be this capacitor. So let's go for this one, and let's see if it will enable us to figure out where the problem is. One thing that is coming to mind is if the diode which supplies this voltage rail from the auxiliary winding on the transformer is short, the shorted diode, then it would make it look like there was a short from here to ground, because what we're seeing in actual fact is the transformer winding, which to DC is practically 0 ohms. So I've desoldered that. Yeah, it's well desoldered. Let's have a look to see where this short actually is. Where? Is it on the board or on the chip? This is ground, G. This is the chip. And it doesn't read short. What's it reading? Is it like most of the other ones? Yeah, it reads very similar to all the ones apart from the one that reads 30 something ohms. So the short, yes, is still here. And I think this is going to be the diode that provides the power on this rail. Let's have a quick look. There's only so many diodes here. What's this one reading? I'll put it onto diode mode. But a short is a short, which is what I'm looking for. So this diode reads short. Yeah, I'm fairly confident that is going to be the one. We can have a quick look, but I'd say so. The other two are zeners. Well, actually, that reads short as well, but that is probably across that voltage rail, so I'm going to lift that one. This one also reads the short as well. Okay, let's lift this one. And let's see, I'll just lift one end, possibly. Let's have a look. Okay, bent a bit of track there, trying to get it out. I think I may have that isolated from the track. Let's see where the short is. So, on the diode, no, so it's not the diode. Where is this short? It's not there. Am I in the wrong place? No, that's the diode that read short. This one. Oh, that still reads short. I think I am in the wrong place. Very easily done. That was like a... No, it's there. Okay, so the short is still across here, but it's not the diode. We'll just double check that to be sure. This should be unsoldered now, just come out. We'll just check that to be sure. Well, you know what I have done, guys, I've actually unsoldered one end of this one and not one end of this one. So I've actually unsoldered the wrong thing. That kind of explains that reading. Right. This is actually a Zener diode. Okay, let's have a look. Have to bend that up, hopefully without damaging the track. You see, this is what happens. You have to bend the thing up and then you damage the track a little bit. Try to get the thing to stay down. Yeah, I have it. Let's see if that's where the short is. Yep. That reads short, the track doesn't. Okay, so I think we found our short as this Zener diode. So look at the other ones now. I'll just lift this one first. Okay, there we go. What do we have? Well, that reads like a diode now. Short has gone. Another one here. Somewhere, yeah, one there. Reads like a diode now. Another Zener here. Yeah, this one. Reads like a... Also reads short. Okay. This kind of ties in with my theory about there being some sort of surge with the MOSFET and the controller turning on for too long, because that sort of thing would cause a high voltage on this rail as well when the field collapsed. That is also short. That would somewhat explain why these Zener diodes have gone. Okay, maybe a problem here. Let's have a look at this. This is the opto-isolator. That reads like a diode, like you'd expect. We can lift this one. Okay, so another one out. What else do we have? We have another zener. Let's look at that. So that's this one. Read short again. Okay. That one is here, ZD901. Let's lift one end of that. It doesn't matter getting enough heat in to melt the solder when you lift the leg. You don't take the pad with it. Okay. Is this short gone off here now? Let's have a look. Yeah. Well, that's open to there. Here, and there should be the short on the diode. Yeah, but not on the pad. That's 3 of them. What else do we have that might be short around here or suspicious? Well, this diode I think we found is okay. This is the one I unsoldered first. Yeah, that reads okay. This will be the TL493 possibly. Let's have a look at you. What are you? K4, oh, C3202 transistor. I think we should check that. Just see what we have. Okay, all the way. Diode, oh, that reads low though. There could be something across it. No. This doesn't look like a transistor. I'm not sure what it exactly is, but it don't look like anything sensible. The fact it's C something or other tells me it's a 2SC something, so I would say that that is gone. C202. If that is the number. Let's take that out and stick it in the component analyzer. I think that is the one, C202. I think the number K432 is not the part number. Okay, what else do we have? We have another diode here. How's that looking? That reads okay. The opto-isolator reads like a something. Let's see. This is the transistor side of the opto-isolator. This is the isolator. This is the LED side. So let's see if we can test it. I showed how to do this on an earlier video. So to test this, we should see a LED on this side. Infrared LED should give us a reading about 1 volt. 0.629, go the other way. Yeah, that doesn't read quite like I expect either, so I'll probably end up taking that out. We can try and test it in circuit. So I have the Eneng meter there. The Eneng meter is an ohms range, this is in diode mode. So we'll connect the ohms range across the transistor side of the opto-isolator, which is here. I'm not sure which polarity, but we can try both. So that can go on there, okay? And then what we do is we have up to see the reading, and it's reading about 100k, okay, about 100k. We then apply diode mode across the LED, trying to light the LED up. I'm thinking, well, this says A, so it's probably the anode. And this is a bit awkward to do because you need 4 hands, but let's see. So I will now connect across here and see what happens on the end. Nothing. Okay, so I'm seeing the diode junction on the opto-isolator, but the transistor isn't turning on, and now slipped. Okay, switch the polarity on the fluke. Okay, nothing's happening on the end. I'm still reading 1000s. Now we're going to switch the polarity on the end. I could look up the data sheet, of course, but never mind. We'll do it this way now. So we'll get connections on here. Okay, read about 1000. You can see it again, and we try to turn the LED on. Nothing happened on the end. All the way around. Nothing. Yeah, so it looks like the transistor is not switching at all. So I suspect we have a faulty opto as well. Okay. Just checking any more semiconductors now here. We have a diode here that did read okay. We have one down here. How was that one? Oh, that one we've already measured. It reads okay. That one. No, in fact that actually reads short. Ah, that will read short because it's directly across these resistors. Okay. We tested that without the resistors. It was fine. And this big one here. Well, that's there. And that reads fine. Okay, opto-isolator out, transistor out. Okay, I'm just on the low voltage side. Now this is the TL431. This is the voltage reference. That obviously would actually be on the low voltage side, so I kind of went off on one then on the wrong track. It happens. When it happens to you, don't worry about it. All the damage appears to be on the high voltage side, and it looks like a surge is blown practically every semiconductor pretty much on this side. Does resistor read okay? Just looks like it might be slightly cracked there as well. Let's have a look. So this is a well, it looks like 3000, like a 3k resistor. That's a bit of a strange value if that is orange. Yeah, unless that's a brown and this is a 10. This is a 1k resistor maybe. Let's see what the resistance meter tells us. Well, that actually reads 3k practically, so it looks like there's a 3k resistor and it reads okay. Question is, what are all these zener diodes doing? Why are there 3 of them? I suspect I'd probably have to reverse engineer this to find out, and specifically why is that transistor there? What's it doing? What is that transistor doing? Well, you can see my peak atlas has fell apart. The plastic housing's broken up where the screw goes in, all of them. And well, the buttons have disappeared somewhere. I can probably fix it. I'm sure it still works. Yeah, it comes on at least. We can use it, but I'll have to do something with it. I think when I took it out, the buttons ended up on the floor or somewhere. I'll try and find them. Otherwise, it's just a walking wounded. That's our transistor. And it's an unknown faulty part. Didn't look good on a multimeter either, so we need the transistor. What did it say about this opto-isolator? I should be able to see the LED. But it's the other side, the transistor side, that looks to be damaged. That's on the high voltage side where all the damage seems to have occurred. So I'm expecting the LED probably will look okay. Yeah, doesn't surprise me. Yeah, 1.13 volts. That's about what you'd expect for an LED. So the problem appears to be on the other side of that. It's not switching, we could see that. My biggest worry though is what value these zeners, do they have values on them? We're going to have to take them out one at a time and have a look. Well, here's the first one. Does it say on it? Is it have any sort of markings we can read? It might do. Well, this looks like it says OC5 or 50C, 0C5. Anything like 1. Maybe a 5.1 volt, I really don't know. We can try with that number up, see if we get any sense out of it. You can see it. 0C51. Let's have a look at the other ones. Well, this one again is marked. I've made a note of which one is which, by the way. So this says Z. I think it's Z22B. 22, yeah. Yeah, that one's Z22B. Sounds like a 22 volt zener to me, that does. And this last one, yeah, this one's a bit hard to read as well, but I looked under the optical microscope also to try and show you guys. But this one says 33. So we have 33 and then B5T. 33B5T. Possibly a 33 volt zener, but 3.3. And the transistor C3202. Okay, so I've looked up these zener diodes. The one that's marked Z22B, I'm fairly confident is a 22 volt zener. I found a data sheet that matches that. 33B5T, I couldn't find a data sheet, but I did get a link to a thread on Badcaps forum about this exact same zener diode, and a few people were asking, and there was a bit of discussion, was it a 3.3 volt or a 33 volt, and somebody did a bit of reverse engineering on their circuit and determined a 33 volt would make sense. So the consensus is that that is a 33 volt zener. This one, OC51, well, I don't know. I can't find any information, data sheet or anything. The transistor, I don't actually have the correct type. I'm sure I could stick something else in there as an equivalent, but why not just see if they've got them in the Capitol on Friday? You know, it's a week's time, but they probably have those things in stock anyway. In the meantime, we need to find out what this zener is. Maybe one of you guys knows and comments below and tells me, but maybe that'll spoil the fun, because I'm thinking, why not reverse engineer this part of the circuit? It's not too complicated. Let's reverse engineer it, find out where that zener diode is in the circuit, and see if we can calculate or presume, come with a sensible idea of what this should be based by its location in the circuit and what it's actually doing. Yeah, I think that'd be fun. Okay, so this video is getting too long to do all that in one go. I know you guys will fall asleep if I leave it for too long, yeah? So we'll leave that one there just for now. Quite a bit more fun fault finding went on there, yeah, and I look forward to seeing you all soon on another Learning Electronics Repair video. Ciao for now, guys.